This projectile motion problem involves a ball being launched at an angle of 36 degrees upward from the horizontal. We're on level ground. We're on the earth. The ball reaches a maximum height of 16 meters, and we're going to ignore air resistance. Here's some questions, some calculations to do. What's the upward speed, the vertical speed of the ball when it's launched? How long is the ball in the air? How far is the landing point from the launch point? So this will be asking to produce a value for x. And then what's the ball's speed when it hits the ground? What's the ball's velocity when it hits the ground? So a number of things to work out here in a projectile motion problem. Be careful to keep x quantities in one equation and y quantities in other equations. The only exception is time. Time is common for both the x and the y equations, but otherwise do not mix x quantities with y quantities in a single equation. Okay, kinematic equations. And we have an assumption here that the acceleration is constant. That's okay for the Earth motion near the surface of the Earth. We have a constant value for the acceleration. And we're going to use separate equations for the horizontal and vertical motions. So these are the four kinematic equations. On the left side, the x kinematic equations, the horizontal motion, and on the right side, the y kinematic equations. We're going to simplify these, but this is the way that we'll start off. For both of them, there's some terminology is similar. X or y without a subscript, that's the final position. X sub naught, y sub naught, that's the initial position at the start of the time interval. V sub x, v sub y, the final velocity. Vx naught, vy naught are the initial velocities. Ax and ay are the acceleration numbers, and t is the time interval. And again, a reminder, t is going to be the same number for the x and y motions. So let's start working on simplifying them. For a projectile motion near the surface of the Earth and ignoring air resistance, why is there no x acceleration? Why is the x acceleration 0? Gravity, the acceleration due to gravity, points towards the center of the Earth. And for a small distance here, we can take this as a level straight line for our launch field. And the acceleration is pointed directly down, so it's 0 for an x component of the acceleration. The y component of the acceleration is downward. Up is going to be my positive direction. So the acceleration is minus 9.81 meters per second squared. So the acceleration in the x quantity is 0. Take a look at these equations, all the places that a sub x appears. So here, here, and here. What happens when we put a 0 in for a sub x? Well, in the first one, the final velocity is equal to the initial velocity in the x direction. There's no acceleration. Speed is not changing. Velocity, magnitude velocity is not changing. The direction of the velocity is not changing. The acceleration is 0. And then the second and third equations, the second equation doesn't have a in it, so it stands as is, but it can be simplified. We'll see that in a minute, but we can even do it right now. These two numbers are the same, Vx and Vx naught, so there'd be 2 times V multiplied by 0.5. That brings us back to 1 times V, and then the t. And here again, this term drops off because the acceleration is 0. This term drops off because the acceleration is 0. So the projectile motion in the horizontal direction is easy. The velocity is constant, and the displacement where we land is just rate multiplied by time, and this is a constant, rate times time. The y equations, got to leave them as they are. So here I've rewritten the left side expressing what happens when a sub x is equal to 0. So you can pause the video if you want to absorb this a little bit, but I'm going to go forward. Here's what we've got to work with for the kinematic equations for projectile motion: the horizontal direction, the vertical direction. All right, let's do this calculation of how fast is the ball moving upward when it's launched. And it's going to achieve 16 meters of maximum height. And we don't need this right now, but the launch occurs at 36 degrees up from the horizontal. But what speed do we need to achieve 16 meters off of the earth, off of the ground? We have a value of acceleration, minus 9.81. Again, negative because that's the down direction. I'm working this with positive as upward. Positive as upward. Well, taking a look at all these symbols, what do we know? What are we given in the wording of this problem? We know the final y position, 16 meters. We're launching from ground level, so the initial y value is 0. At the top of the motion, is the ball going to go any higher? No, we're at the maximum height. Consequently, the motion in the vertical direction is 0. For an instant, the velocity in the y direction is 0 at the top of the motion. We do not know the launch speed vertically. We do not know how much time the ball is in the air. So take a look at these equations. Take a look at this data. Might want to pause the video. Which of these equations is going to be useful if we want to calculate v sub y naught? The fourth equation doesn't have the time. I'll just flip back to that for a minute. The fourth kinematic equation doesn't have the time. Time is unknown. So we pick an equation that does not have the time but does have the quantity we're interested in, the vy naught. Let's put in our data. 0 for the final y velocity, minus 9.81 for the acceleration, 16 meters for the final y position, 0 meters for the initial y position. And you might want to pause the video and try this on your calculator. But the 16 times minus 9.81 gives us 313.92 meters squared per second squared. And adding 313.92 meters squared per second squared to both sides, you get this equation. Take a square root of both sides. I take the square root, the numeric value is 17.72. The units switch from meters squared per second squared into meters per second, as they should. And I'm going to round off here. Typically, I keep 3 digits in my answer, 3 significant figures. Ask your instructor what the preference is for rounding. And now this is the speed. I'm not giving a direction here. The direction's upward, but we're asked for the upward speed, and that upward speed is plus 17.7 meters per second. The second question, how long is the ball in the air? Well, we just found that the initial velocity is 17.7 meters per second. We also know at the top of the motion the y velocity is 0, and we know the acceleration. So the first kinematic equation will be able to give us this time moving up. This is only a calculation from ground up to the maximum height. So 0 for the final velocity, 17.7 for our initial velocity, our acceleration. We can calculate the time. Again, pause the video and pull out your calculator. I came up with the time required to move up is 1.804 seconds. Now we're doing this with no air resistance, and there's symmetry in this problem. If we start at ground level, go to a maximum height, we have a certain time. The time to come back down from the maximum height to the ground is the same as the time going up. Again, no air resistance. So the time in the air, the total motion, is just twice the time to go up. And again, I've rounded to 3 digits here. 2 times 1.804 is 3.61 seconds. There is another method to calculate. I got a little carried away on my spacing here. But to calculate the time in the air, this is another method. we know that the launch speed upward, the original Vy naught, is 17.7 meters per second. And we know the final velocity is 0 at the top and of the y direction and the acceleration. So take a look at the third kinematic equation. The third kinematic equation. If we let the start of the problem be at the ground, so y naught is 0, and the final point of the calculation again be at the ground, 0 meters. So we're doing the full event from launch back to impact with the ground. Our initial velocity in the y direction, we worked that out earlier. We've got time in the air. We've got our acceleration and time in the air squared. This is quadratic, but it's simple to solve. Factor off time in the air. Factor off time in the air. And when you do that, you'll have time in the air times the quantity 17.7 meters per second plus 0.5 times minus 9.81. The first factor has to be 0 to produce a 0 for the multiplication. And the second one gives us the equation 0 equals 17.7 meters per second minus 4.905 meters per second squared multiplied by time in the air. You can solve this with your calculator. Divide 17.7 by 4.905 and you come up with 3.61 seconds, and not surprisingly it agrees with the first method. I'm going to flip back to the first method. We got 3.61. This method, 3.61. Question 3. How far do we land away from the launch point? We're on level ground. Our key concept here will be that the time moving in the x direction is the same as the time moving in the y direction. There's only one ball, so these two times are the same. T sub x equals T sub y. That's typical for projectile motion problems. And the distance traveled here, the range, the x direction, is just the rate multiplied by the time. Well, we just found the time in the air. How can we find the speed in the x direction? How can we get that? Well, we have a right triangle to work with. We know the angle over here is 36 degrees. We know the Vy naught number. Well, given this number and the 36 degrees, I'm going to do some unnecessary steps here to remind you of some trigonometry, but we'll get to a simpler way to calculate it in just a minute. The components here. The x component of the velocity is equal to this launch velocity v naught times cosine theta. That gives us the x component, the adjacent side to the 36 degree angle. The sine calculation will give us the opposite side to the 36 degree angle. Will give us Vy naught. So we don't know V naught, but let's write out those two expressions here. How we calculate the x component of velocity, how we calculate the y component of velocity. Again, V naught appears in both of these equations. So let's solve both of these for V naught. If I divide both sides by cosine theta, I get this expression. The second equation, divide both sides by sine of theta, we get this expression. So I have a quantity here equals V naught. A quantity here equals V naught. They're the same. So Vx naught divided by cosine theta is equal to Vy naught divided by sine of theta. If I rearrange this just a little bit, multiply both sides by sine of theta and divide both sides by Vx naught. We now have this expression. And now sine of theta divided by cosine theta, that can be replaced with tangent of theta. So tangent of theta is Vy naught divided by Vx naught, or Vx naught, the number that we're trying to come up with here, our speed in the x direction, is equal to our speed in the vertical direction divided by tangent theta. We know the theta, or a given 36 degree launch angle. Earlier we found Vy naught, so plug those in. I got 24.39 meters per second. That is the x speed. And now I'm using a little bit more accurate time number. Instead of 3.61, I'm using 3.608. We found that earlier. Multiply those two, we get 88 meters for the x. I'm rounding off just a little bit here. So typically, again, I keep 3 digits in my answer, but an x of 88 meters. What's the ball's speed when it hits the ground? Well, in the y direction, the velocity is just going to be negative the launch y velocity. It's going up when we launch. It's coming down when we land. Down is a negative number. Speed is the square root of the squares of the two components added together. So we just found these numbers. The 24.39 meters per second, if you recall, we found using this overly complicated. I could have, if I go back here, if we know Vy naught, we know 36 degrees. If you're familiar with trigonometry, you would not bother with all the work I did. You would just say tangent 36 degrees equals this number divided by this number, and you do the calculation. But I wanted to review the right triangle a little bit and the sines and cosines for you. So our speed is the x speed squared plus the y speed squared, and take a square root of that. It's 30.1 meters per second. When we're asking about the velocity, we need more than the speed. We also need direction. A velocity always has a direction. To find that, again, we're going to be involved with an inverse tangent function. The angle is equal to the inverse tangent of the y component divided by the x component. We have those numbers. The y component is minus 17.72. The x is 24.39. You should make a little sketch and realize this is a fourth quadrant number. X-axis goes along here, first quadrant here, second quadrant over here, third quadrant here, fourth quadrant around here, going counterclockwise from the x-axis. So your calculator will tell you, if you're in degree mode, it will tell you minus 36 degrees. In terms of a positive angle, it would be 324 degrees counterclockwise from the x-axis. So I could say the velocity is 30.1 meters per second at an angle of minus 36 degrees. Or if your instructor wants you just to use positive angles, then you would report 324 degrees. But speed has no direction. Velocity has a magnitude, a speed, and also a direction. So some of the key concepts here. You'll be helpful to yourself, and you only get the right answer if you put x quantities in one set of equations and y quantities in another set of equations. Do the horizontal and vertical motions separately. A typical problem, the acceleration of the x direction will be 0 for projectile motion, and no air resistance. So the speed in the x direction will be a constant, the velocity will be a constant, and distance equals rate times time. Distance equals rate times time. The value of time is the same for the x and y equations. In some problems, you'll use either the x or y equations to come up with a value for the time, and then you'll use that time in the other set of equations, either the x or the y, and complete the calculation. So be aware of that connection. The time variable is the same for the x and the y equations. For more videos on sample physics problems and some short physics lectures, I have them listed at gpclements.com, gpclements.com. The annotation of groupings of these for various topics of physics, and in that annotation you'll find a title for the video. You'll find a direct link to YouTube where you can play the video. You'll find how many minutes the video lasts and a little description of the video. All this content is free, no charge. You do not register, you do not give me your email address, you do not give me your name, etc. And my website does not put cookies on your computer. So keep working physics problems, ask your instructor questions.